Okay, let's start. So what we're going to do is to define all those kind of calculation we require for Locus. The first thing we talk about is this is what? Characteristic equation, which we talk about, I think in PID controller, we talk about characteristic equation. So when we are dealing with this one, before we do the negative one, what do we have? We say we have a denominator, we have numerator. Denominator is a combination of poles. Numerator is combination of zeros. So assume we can separate everything as a single poles and zeros. What we're going to do is we have s minus p1, s minus p2, so far and so on, and assume we have n poles in the numerator, and we have s minus z1, s minus z2, and we have m zeros. Keep in mind, m and n, they are not the same because normally we have more poles than zeros. But if you do something like this, I can tell you it's not going to be the same because we still need to have another thing, that is k. I think we talked about this earlier, right? This is what? System gain. And we have poles and zeros. So this is going to be the thing we're going to talk about. So before we move on, let's talk about my poles or vector. It doesn't matter you are using poles or zeros. When I have a pole or zero, we are having real part plus imaginary. So if you have first order equation, this one is going to be 0, but everything remains the same. Or this one over here is going to be R, E, J, B. Okay? Or in other words, it's going to be R cosine phi plus J sine phi. It doesn't matter what you do, it's going to be the same. Right? So if we put that in polar plot, you guys still remember this, right? This is a engineering mathematics. Some people tell me you guys don't remember this already. So this is just a reminder of everybody. So if we are talking about a complex number, this is how we synthesize those kind of stuff. And you see the omega over here, it's actually the phase, not natural frequency. They are different. Normally I would prefer to use phi instead of omega, but if phi is used for exponential term, omega is used for complex conjugate representation. Sometimes you might use cosine and sine term to represent everything, but it doesn't matter what you do. Those means the same thing. Okay? So when we are dealing with something like that, my G, H, S. It's going to be K remains the same. And I have my magnitude. I have exponential J D Z1. Second part is going to be S minus Z2. Exponential J B Z2. I'm not going to write down everything, but essentially it's going to be something like that for the part of the numerator. Is that clear? It's from what I'm developing over here to this one. I'm going to use this one because this one is my magnitude part, and this one is going to be my phase part. I need to separate them into two parts. One is magnitude, the other one is phase. I'm going to explain why I need to have this one. So for the denominator, I have same thing. Okay, so if we do everything, we can separate that into two parts. S minus Z1, S minus Z2. Right? I still miss something, which is the phase, or the exponential part over here. So since I do exponential over here, what do I have? I have, okay, VZ1 plus VZ2 plus I don't have enough space, so I just put the exponential term over here, okay? Until I have V, Z, M. Since I have M, Z, zeros in the system. How do I deal with the phase in the denominator? This is the numerator, so I add them together. This is the denominator, so I what? You really forget engineering mathematics. We're going to have negative or minus. Remember?
Yes.
Yes. Now you remember, right? Okay, good. So overall, I'll have negative 1 for everything. We all have, since this part over here, they are absolute value, right? So can this part be negative number? No, this must be positive, right? Since it's what? Absolute value. So this, everything over here is going to be positive, which means this part over here must be 1. I have a negative sign over here. It's going to be over here, negative 1. When I say it's negative 1, can you tell me the angle? I know you can't because you forget engineering mathematics.
180.
Very good. So this part is positive, this part is negative. This one is how much degree we're talking about? 0. How much we're talking about? 180. 180. So you can say it's going to be positive 180 or negative 180 degree. It doesn't really matter because it's the same. Make sense? So we're going to use this. Normally we just use negative 180 degree. It doesn't really matter, but for some reason people tend to use negative 180 degree or pi. Okay, so 2 negative. The system stable. One plus G H S equals to 0, which yield G H S equals to negative 1. Magnitude, which is this part, equals to 1. Phase term, is this always, when I say it's negative 1, do I have 180 degree only? If I rotate from here to here, it's -1. If I rotate another 180 degree, it becomes what? 1. But if I rotate for another 180 degree, what do I have? -1. So when I say it's -1, it's not always 180 degree. It's actually odd. Not pi. So what I mean is it can be 180 degree, it can be 540, it can be 800, 960. No, 900. Then you so far and so on. You just keep on adding 2 pi together, so it's going to be pi, 3 pi, 5 pi, 7 pi. It is always -1 based on what you see in the polar plot. Does it make sense? So that is how we're going to fulfill the magnitude criterion and phase criterion. This is called magnitude criterion, and this one is called phase criterion. Any question? So since we don't have any, this one is pretty straightforward, right? So since we agree this part over here is 1. Let me ask you a question. If you take the absolute number over here, what are you going to get? 1. Because the radius of individual one is going to be 1. That's the definition of a polar plot, right? So if individual one is 1, you take the absolute value for the whole chunk over here, it's going to be 1. And the other side is going to be 1. So this part can be canceled off on 1 since it's 1. Right? That's means K of the overall system is going to be inverse of this thing. Make sense? This is 1, this is 1, so K can be obtained by put this one in the denominator, in the numerator, and this part in the numerator, in the denominator. That is going to be so we can calculate what the K is going to look like. This is also something we call magnitude criterion. Now, over here, I'm talking about the exponential term over here, but when we are putting everything together, we don't really want to do something like this. So when we are dealing with something like that, we want to have I equals to n to the number of z. If you add all the phase of the zeros together, in this case I'm using n, but when you are looking at your textbook, I think it's nz. Minus the phase part. Equals to what? From now on, you need to get used to a specific term. I know it's going to be pi, but we're not going to use that one. We're going to use plus minus 2n multiplied by 1 because this one is always an odd number. N is going to be 0, 1, 2, 3. Right? So this guarantees everything is going to be the odd multiplier of pi. It can be 180, 540, 900, so far and so on. And it doesn't matter, it's positive or negative. they are the same phase. Any question? So the other thing you might find in your, I'll let you guys write it down. So the other things over here, after you put down the this is angle criteria. You are using this one when you are dealing with Locus, and you're going to use this one when you are dealing with frequency domain controller design. You're going to deal with magnitude criterion and angle criterion again. So those two is going to be design criterion for Locus and frequency design. The other thing you're going to find, Locus starts at open loop pulse, just like what we did earlier, for k equals to 0. The reason I explained to you is that though it's closed loop, but if you reduce k to 0, we don't care about the zero part, the closed loop 0 part or the closed loop numerator part. The denominator is going to be my transfer function. If k equals to 0, it's actually the same as the open loop pulse of the transfer function. That is something we explained earlier. And when your k start to increase, when it gets to infinite, it's going to end at open loop zeros. It's not going to show up over here, but when you are drawing your Locus, including both zeros and poles, you're going to find out when your k equals to infinite, it actually get close. It will end at the open loop zeros. That is something we're going to talk about. The other thing that we might talk about is proper transfer function. Proper transfer function is straightforward. When we say it's proper, the number of zeros must be smaller than the number of poles. That is something we call proper. If NP is greater than the number of zeros, it is a proper transfer function. If it's not equal, if it's still equal, the number of poles equals to the number of zeros is still proper. If the number of poles is greater than the number of zeros, it's strictly proper. If it's equal, it's called biproper. I don't want to read those parts, just making me feel bad. Just read this part, okay? I just don't want to read that. So they have their own definition, and when you have those kind of things, the first thing you guys need to remember is what are how many asymptotics you're going to have. So do you guys still remember? When I have two poles as my open loop system, what are the Locus going to look like? Get together and break away. 90 degree and 90 degree. I'm going to tell you the zeta. This is something we call zeta. Okay. It's going to be plus minus number of poles minus number of zeros. Which means if I have 3 poles, what I'm going to have is I'll have, if you divide this one, what do you going to get? 60, 180, and negative 60. Or you divide 180 by 3. So what you're going to have is start from here, and one is going to this direction. One is going to this direction, and the other one goes to this direction. The other one goes to this direction. That is how you use this formula. And this is the first formula you're going to encounter. Any question? Yes, I believe it's a lot of questions. So if you have, I'll give you some kind of purpose. If you have whatever s plus omega n squared. So you have how many poles you have?
3.
How many zeros you have?
1.
So when you put everything together, how many? This is going to be 3, and this is going to be 1. So eventually, this is going to be 2, and 180 divided by 2. So you're going to have 1 here, 1 here, 1 here, and 1 here. Let's say 1 here. I think it's going to be something like this, and this one goes to this one. Don't worry, I'm going to tell you how to calculate those kind of things. But this is an important but. When you look at this one, the trajectory must be 90 degrees. I don't care. The reason I'm doing this is because you only have 1 zero, right? Yeah. 0 is going to be the end of what? Pole. So if you put this one end at this one, where is this one going to be ended? They are symmetric. You cannot say this one ends over here and this one ends over here. It doesn't make sense. You only can 1 0 can only attract 1 pole. So you cannot say this one is going to attract this one and this one. It doesn't make sense because you have 2 poles. Right? So this one have no choice but attract this poor one over here. Okay? So this one and this one have no choice but gets to positive 90 and negative 90. It can be this direction, it can be this direction. But no matter what you do, it must be positive, negative 90 degree. And the other thing is, when you are drawing your locus, they will not cross from each other. Which means if you are creative and you are art, you are artist. You say, I want to do this thing, and this one is going to do this thing. You cannot do that. They are crossed out. They are crossed with each other. You cannot do that. They cannot intersect at all. Okay. So that there are a few rules over here. Yeah. That's. So if you say I have S how many poles we have?
5.
How many zeros we have?
2.
So what are you looking at? Are you going to look at plus minus? No, right? You must be 60, negative 60, and 180. So it must be something like this.
Yes.
So rule number 1: calculate the difference the number difference between pole and 0, and divide the 180 by the difference. Then determine what it's going to look like. Because that's a mistake a lot of people make. Well, I believe it's not from you, but that's actually a lot of something when I was teaching in other university, this is a very common mistake. Okay, so sometimes, even though it is 3, number is 3, but you still draw something. The reason is, Professor, you always draw something like this in class, so it must be like this. Okay. Okay, that's not the reason. So if I say it's going to be what are you looking at?
45.
45. 45. 186. 135. 225, negative 45. So we're going to calculate this position later. It's going to be our centroid. Okay, so those are the things you guys need to remember before you start to do everything. Okay, depending on what you have, determine how many asymptotas you're going to have. Then you start to draw your rules. Okay. Any question before I move on? Second thing we're going to talk about So the second thing we're going to talk about centroid of roots. So we know it's going to break out at certain place, goes to plus minus 90 degree or 60 minus plus minus 60 degree and 180 degree. So where is the point you're going to have those intersection? All those trajectory going to be intersected. That is something we define as OA equals to value of poles minus value of zeros divided by MP. Okay, pretty straightforward because the previous one, I'll show one thing to you. Do you guys remember the one we used in the previous class? This is -1, this is 0. The S plus 1 K problem. So open look, my poles are located at what? 0 and 1. How many poles we have? How many poles do we have? 2. How many zeros do we have? 0. So the denominator over here is what? 2. So the number, the summation of the poles over here is what? -1 plus 0. So I don't have any 0, so the numerator over here is going to be -1. If you divide that by 2, where are you going to, which number you're going to get? -0.5. So when you draw the rulers over here, where is the breakout point? Where is they going to be intersected? Do you guys remember what I'm talking about? So this is how we calculate using formula. You can draw that point by point, but I don't believe you want to do that. It's just tedious, unless you have MATLAB. However, MATLAB is $3,000 US dollars if you buy that when you are not student. So I don't believe you want to buy that, right? If you ask your boss, say, okay, I want to buy MATLAB. I have 3,000 for MATLAB itself, 3,000 for Simulink, and each 12 bucks costs you $500. Believe me, your boss is going to fire you right away. So that's a good thing to do. You can use Python. Python is pretty much can compensate for all the MATLAB can do. But anyway, so this is how we, before you can generate, you want to do anything point by point, you can just use those formula to find out what is the direction of your locus and where is going to be the centroid of everything. Those are the first two formulas you guys need to remember. So far, any question? No? We're going to have maybe more than 10 formulas you guys can remember to draw. Seriously. Well, I think sometimes it's more. Yeah, it's going to be a lot. Okay. So let's do a little bit practice before we move on. So if I have a transfer function like this, open loop. So can you tell me what are the angles of all the asymptotics over here? Three. Yeah, I have 3. What are the angles? 60, minus 60, and 180. Right? So I have at 2, 3, and -10. So can anybody tell me where is the centroid? -5. Okay, so we know it's going to be 1 goes to this direction, 1 goes to this direction, and 1 goes to this direction. What are we going to draw that? Are you going to, we know they are not going to be attracted from each other, right? Poles must be n at 0. But we don't have any 0 over here. It means that those 3 are going to be infinity. Right? All the poles goes to this direction, and this direction, and never end. And the other rule is, when I start to draw asymptotics, can they intersect with each other? No. You can't. So what are you going to do? Are you going to have this 1 point to infinite? No. Are you going to have -2 point to the infinite? No. Which one must be goes to the infinite? -10 one, right? So we know this one is going to be this one. So how are you going to draw those 2? Are you going to put those 2 point to this direction? No. Because if you do that, this one goes to this one, it's not a big deal. But when you have the -2, what happened? You are going to intersect with the other locus, which is prohibited when we are drawing something like this. So what are we going to do? One must go to this direction, and one must go to this direction. And we know it's going to this direction, and those 2 are going to be hit to each other. And at some point, it's going to be breaking out, breaking out. Okay. So far, any question? Does that make sense? No? Yes.
他们会互相。
关掉。